purpose of this animation is to illustrate the relationship between two phasors in a rotating phasor system. So before this one makes sense, you really should watch the video that relates a phasor quantity as we understand it to represent a voltage or current to a rotating phasor and how that relates to the cosine trigonometric function. This this will make a lot more sense if you watch that video first. So what I want to illustrate is that here we have two phasor quantities. Um, we have one that has a magnitude of 6 units, and we have a second that has a magnitude of 3 units. And they're spinning together at a rate of zero point 0.1 hertz, or uh, I'm not sure what that is in radians per second, but 0.1 hertz means that it takes 10 seconds for these um, vectors to rotate one time around the polar plot here. If I change the system frequency, let's say to something higher, such as 0.5, that'll take 2 seconds for them to rotate. You can see they speed up. And then I could come over here and I could change that to 0.01. That'll slow them down. It'll take 100 seconds for them to rotate around one time. You can see that's really slow. So uh, for us visually, I think 0.1 works pretty well to illustrate um, the rate of rotation. It's not common in electrical systems to have a frequency that slow, but if we were to up this to, let's say, something slow, even like the power system, 60 hertz, we can see that's pretty much too fast for us to even make sense out of visually. So we're just going to use a much slower than normal signal to represent what we're talking about. So it's kind of obvious, but I'd like to point it out that they're rotating at the same rate. That's because I'm graphing two different cosine functions that have the same system frequency f, right? The omega term in both of these cosines is the same, and that means this is a synchronous system. You know, we're dealing with systems in which the frequency is fixed. When we write phasor quantities or draw phasor diagrams, we typically eliminate this frequency and we just keep it in the back of our mind. Oh yeah, the system frequency is 60 hertz or something like that. But the rotating phasor actually is a manifestation of that frequency. We can see that both of those vectors are spinning. This big one might represent a voltage, this little one might represent a current, and their instantaneous value is a function of time. For both of these vectors, the instantaneous value is the projection of the vector onto the x-axis. We've already talked a little bit and illustrated how the amplitude changes, and what this diagram and animation is really meant to illustrate is what the phase shift means in a system of rotating vectors or phasors. And so I've arbitrarily chosen a phase shift between these two vectors of 30 degrees. We might say that the voltage waveform here is uh, leading by 30 degrees. So we can see that it's out in front leading. It's out in front of the voltage waveform here. So we'll say phasor 2 is a voltage and phasor 1 is a current. So right now we got a current that's leading a voltage by 30 degrees. Well, what if the current was leading the voltage by 60 degrees? So we can just update that. We see that there's a big jump here, and we see that there's a 60 degrees of phase shift between the two rotating vectors. And that stays constant because they're rotating at the same rate. So that's why we say it's arbitrary which one's taken as the reference, because really what's important is the difference between these two angles, or these two vectors. And the difference always stays the same. Their instantaneous angle might be changing as they rotate, but if I subtract the angle of the current from the angle of the voltage, I always get a constant number. And so that fixed phasor number that we write on a piece of paper, say 5 volts at angle 0, or let's say 6 volts at angle 0, and 3 amps at angle 60, I can see now how that relates to the fact that even if these things are rotating, that's an accurate representation of the system, because really what we're concerned about is the relative quantities to one another. Right? So right now what I'm illustrating is called a leading system. The current is leading the voltage. We'll talk about that a lot more in the class, but what if I wanted a lagging system? What if the current was behind? So now you see that this voltage waveform here is in front of the current waveform. And by in front of, I mean its value reaches the positive x-axis first in the rotation as it rotates counterclockwise. Typically, this phase angle in power systems is from 180 to negative 180. You won't see values such as, you know, 270 degrees. We typically won't do that. So hopefully this video helped, or this animation helped you recognize the relationship between two rotating phasors in any sort of electrical system.